Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to look at the Markov decision process more formally. We've essentially been looking at Markov decision processes this whole time, just never calling it by name. Any reinforcement learning task with a set of states, actions, and rewards that follows the Markov property is a Markov decision process. Formally speaking, a Markov decision process is a 5-tuple made up of the set of states, set of rewards, set of actions, the state transition probabilities, and the reward probabilities, which we previously discussed as a joint distribution, and the discount factor, which we'll define in a later lecture. There is, however, one more piece we need to complete the puzzle. The other key term in Markov decision process is decision. The way we make decisions for what actions to do in what states is called a policy. We usually denote a policy with the symbol pi. Technically, the policy is not part of the MDP itself, but it's part of the solution along with the value function, which we'll define more formally soon. The reason I've left out the policy until now is because it's kind of a weird symbol. We write down pi as a mathematical symbol, but there's no equation for pi. For example, if pi is epsilon greedy, how do we write that as an equation? It's more like an algorithm. The only exception to this is when you want to write down the optimal policy, which can be defined mathematically in terms of the value function. We'll talk about optimal policies and what that means in a later lecture. So for now, pi is more like a shorthand notation for the algorithm the agent is using to navigate the environment. Because a Markov decision process satisfies the Markov property, you can imagine we can also draw state transition diagrams for MDPs, just like we do for Markov models and hidden Markov models. I don't do this often, but you may find it useful for yourself. Let's look at the state transition probability again, P of S prime given S and A. Recall that I said this is typically deterministic, but that's not always the case. Why might that be so? Remember that the state is only something derived from what the agent senses from the environment. It's not the environment itself. The state can be an imperfect representation of the environment, in which case you would expect the state transition to be probabilistic. For example, the state you measure can represent multiple configurations of the environment. As an example of an imperfect representation of the environment, think about blackjack. You might think of the dealer's next card as part of the state, but if you're the agent, you can't see the next card, so it's not part of your state. It is part of the environment. Let's look at actions too. When we think of actions, we think of joystick inputs like up, down, left, right, and jump. We think of blackjack moves like hit or stand. But actions can be very broad as well, like how to distribute government funding. So reinforcement learning can be applied to making political decisions as well, and it probably is. Sometimes there's confusion about what constitutes the agent and the environment. Think of yourself navigating your environment. You might think you are the agent, but what constitutes you? Are you your body? Your body is more correctly part of the environment. Your body isn't making decisions or learning. Your body has sensors which pass on signals to your brain, but it's your brain or your mind that does all the learning and decision making. So you want to be mindful of where you draw the boundary that differentiates between agent and environment.